Okay.
Small.
Perfect. Clicker. Okay. Apologies to Sean, who has already seen this presentation from my graph algorithms talk on Tuesday. I didn't have enough time to make a new presentation for Sigma, so we're getting this one. This will be a bit quicker, but I think it shows some kind of nice applications of graph partitioning to real world problems and some interesting kind of approaches that work well in practice, but we don't really have good like theoretical bounds for. Okay, so the problem we're trying to solve is we have this thing that we call a hypergraph. The idea here is that an edge can be incident to more than two vertices. So you can see on the top, we have this circle-looking thing that has three vertices in it. That circle is one edge. So edges are sets now instead of just tuples, and there's no notion of direction. So an edge is just a set. And what we want to do is we want to find some way of cutting this hypergraph into two pieces. Like I drew this line here that separates into two disjoint sets of vertices. And some things that we want to think about when we're solving this problem are how well balanced is this partition, right? We don't want to have one vertex on one side and all the other vertices on the other. And we also want to think about the cost of this partition. We may assign some weights to the edges, and we don't want to cut an edge that has a really big weight. So we want to simultaneously achieve balance as well as minimum weight. So more generally, if we have k partitions instead of just cutting it into two, we want that the number of nodes in each partition is at most 1 plus epsilon times the total number over k. So if we were to divide it perfectly, every partition would have exactly n over k nodes, but we'll allow a little bit of wiggle room, epsilon amount of wiggle room, to maybe make our cut cost cheaper and make it easier to do this algorithm. Because if we're trying to do it exactly, it's just going to take too long. Even with this epsilon constraint, this problem is NP hard. So that's a little unfortunate because this is something that shows up in practice a lot, which I'll talk about in a little bit. So what the subject of this talk will be about is we have this NP hard graph problem, and even approximations where I allow this epsilon factor are NP hard. So what we need is an algorithm that runs in polynomial time, but probably doesn't give us an exact guarantee that we will adhere to this approximation, but in practice will actually do pretty well. So why do we care about this? The reason that I'm interested in this and am working on this project is this idea of data partitioning. So if you think about sparse things, for example, maybe you have some matrix or some Boolean formula. Most variables in a Boolean formula don't appear in every clause. They appear in 2 or 3 clauses. So they're kind of sparse in that sense, where if we use an edge to represent a variable, and that edge is incident to all of the clauses that contain the variable, each edge would not have too many vertices. Other cases include if we want to do sparse matrix multiplication, you can do some sort of hypergraph where you have like rows as edges, columns as vertices, and you can use this to figure out how you might want to break up your matrix across multiple computers if it is sufficiently large. And the case that I care about is in compilers. Compilers, at a high level, you can just think of a compiler as turning a program into a bunch of nodes in a graph. And if you move a little thing along that graph, it will compute the output. So this graph here is not very visible thanks to the projector, but in essence, this is a program that adds two vectors element-wise. So this is a pretty sizable number of nodes for an operation as simple as element-wise addition. So we care about being able to do fast operations to this compute graph. So in traditional compilers, if you think about running GCC or Clang on your laptop, it just generates code for the CPU. Likewise, if you write CUDA, it just generates code for the GPU. But the compiler that I'm working on with some folks in the LLVM group, what we aim to do is we want to automatically split up a program between multiple accelerators. So if you have a CPU and a GPU in your system, some of the matmals and stuff that your program is doing should be assigned to run on the GPU, and some less compute intensive stuff might be better run on the CPU. And the question we want to solve is what code goes where. And the way that we plan to do that is with hypergraph partitioning. So the idea is that right now we just have some graph representing computation. And multiple nodes in this graph can map into a single hardware instruction. You can think of this as, for example, if I have an addition, let me see if I can find one here. Here's an addition that has some inputs. And the addition and its inputs might be mapped into a single CPU instruction. Likewise, an entire loop that does a matrix multiplication could be mapped into a single GPU instruction. So we have this scenario of multiple nodes can be mapped to multiple different ways of lowering code onto a device. And what we'll do is we will create a hyperedge that represents each of these possible lowerings of code onto a device. And given these hyperedges, what we want to do is figure out the fastest way to execute the code. Meaning, if we assign each edge a weight such that if the lowered code would be really fast, think about a matrix multiplication on a GPU, that edge has really high weight. We definitely want that to be on the GPU. We don't want to break up that edge. And similarly, if an edge has low cost, that means there's probably nothing too bad about breaking it up. So we reduce the problem of mapping code onto devices to the simpler problem of partitioning a hypergraph that has weighted edges. So now the question is, how do we do this, right? We know this problem is NP hard. We know approximating it exactly with a guarantee is also NP hard. So we need a practical algorithm that works well and that doesn't strictly adhere to optimality guarantees. And the way that a lot of papers do this is this three-phase approach, where we do something called coarsening, then we do initial partitioning, and then we do uncoarsening. So let's start with the example graph that we had before. So in the coarsening phase, all we do is we complete some number of steps, where in each step, we pick some vertices and merge them together. So in this case, I'm going to pick the top three vertices, and I'm going to merge them into one new vertex. That one new vertex shares any incidence to edges of the original vertices. In this case, those vertices were just incident to this larger edge. So that vertex becomes a member of that edge. I can do this again. And here in the middle, I started with these three vertices, and I'm going to perform a coarsening here. So the edges that these are incident to are this edge, this edge, this edge, and this edge. And we see that the new coarsened vertex is incident to all of those edges. And we could do this again until we get to a smaller graph. And the way that we actually do this coarsening is something that different papers focus on figuring out ways to optimize this. So I'll talk a little bit more later about how we can decide what vertices we actually want to coarsen. But once we've done this, and we have a small enough graph, we're kind of at a base case. We probably have 200 to 300 nodes. And at this point, we'll do what we call initial partitioning, where we, by some metric, figure out a good partition for this smaller graph. This graph is small enough that we can run a pretty high quality hypergraph partitioning approximation on it. And we get some partition that looks something like this. Now, one thing to note here is that I drew these coarsened vertices bigger. That's because when we are considering balance, what we do is we assign these coarsened vertices a higher weight than uncoarsened vertices, so that a balanced initial partition will still be balanced after we undo the coarsening step later on. Now, before I continue, does anyone have any questions on how we got to this initial partition? Yeah.
So is it when you do the coarsening, does the final coarsen graph have to be a hypergraph? You can force until you don't end up with a hypergraph. Does that make things very easier?
You, in theory, could coarsen until you get something that is not a hypergraph. In practice, that doesn't necessarily happen just because of the structure of the input graphs. Your coarsening algorithm would have to do a lot of like global search of the graph, and that's not the best for performance. So people typically do some sort of like local search during coarsening. Yeah.
At least before the coarsening, the top left, like bigger vertices, it was split into 3 smaller vertices, only one of which was inside that bigger edge. How do you like determine whether one of them should go in or should not?
We take the union. So we look at all of the vertices that we are coarsening and say, what is the union of all of the edges that are touching these vertices? And that big list of edges, all of those edges will get the coarsened vertex. It works in practice. That's kind of the theme of the talk, is some of these decisions are kind of arbitrary, and it's because some guy in Germany decided to do trial and error and found that this worked better. All right, any more questions before we, this has been skipping out, okay. Any more questions before we move on to uncoarse? All right, so now we want to get back to a partition in the original graph. So what we'll do is we'll go in reverse order of the coarsening that I did. So the last vertex I coarsened was this one. So let's go ahead and uncoarsen it here. And we see that this edge doesn't cross our partition boundary. So uncoarsening here is going to have no impact on the cost of this good initial partition. Now let's go ahead and uncoarsen again. And now I've added this vertex here that is on edges on both sides of the cut boundary. So we want to consider whether or not this middle vertex that's right up on the boundary should be moved to the top of the boundary or should stay on the bottom. And we'll do some sort of local search algorithm, which we'll get to later, to decide how we should do that. And in this case, the algorithm tells us we should move the vertex. So we'll move it above our partition boundary. We'll move it to the other side of this partition. And then we can continue. We'll uncoarsen at the top. And now we have some partition that is hopefully pretty good. But we don't have any guarantees. But in practice, this works well, and it can be made very, very fast. Some recent, like the current state of the art, you can partition hypergraphs with 2 billion edges in like not very many seconds, which is pretty impressive if you're willing to throw enough compute at it. So this is kind of a fairly straightforward approach, but picking how we do the initial coarsening and how we do the uncoarsening and how we get good performance is pretty interesting. So let's First, take a look at the initial partitioning. The way that current state of the art does this is kind of stupid, but works very well. It is to say, I'm going to pick 9 different partitioning algorithms, and I'm going to run them all 20 times because they're all randomized. And this gives me 180 initial partitions. I'm just going to pick the best one. That's all they do for computing the initial partition. And then the interesting part becomes, how do we do coarsening and uncoarsening? What most modern papers do is they have n coarsening levels where we go in n stages, where n is the number of vertices in the graph, roughly, and we just merge 2 vertices into 1 at every step of this process. So we do this to get down to a hypergraph of about 300 vertices. So this takes us n minus 300 iterations. And then when we want to do the uncoarsening, we need to have some data structure that keeps track of what vertices we have removed during coarsening so that we can undo that and do local search. Yeah.
How do you decide which like vertices to merge together?
The way that they do that is by looking, they define a metric based on edge weight, where basically if you merge 2 vertices together, you want them to be on edges that are like of low weight. And I think they do it based off sum of weights of all the edges that a vertex is incident to. Now, the problem that we were solving was, how do we split a graph in 2, right? Now, what we actually want to do is we want to split it into k parts. And we have this epsilon amount of imbalance allowed. And I won't go through the algebra because it's kind of painful. But the idea is that we actually allow more imbalance than we need. So let's say I want to split into 5 pieces. What I'll do is I'm going to, instead of using a small epsilon, I'm going to multiply epsilon according to this formula. And it will allow me to get a partition that looks like this. Now, keep in mind, epsilon is like the worst case kind of imbalance, but in practice, what happens is that these algorithms will almost always return something that is very, very close to the worst case. So we can assume that we'll get a big partition and a small partition if we increase epsilon. And now I cut this in 2. And now I want to solve the problem of splitting this one up into 3. So we can compute a new epsilon value. We'll get something imbalanced. This one we split into 2. So by picking larger epsilon, we're able to start introducing odd numbers, and then we can just recursively divide until we get to our base. So the way that we do coarsening is the kind of weight idea that I mentioned earlier, which is we keep a priority queue of all of the vertices, keyed by this function R, which is a measure of weight of incident edges, the average weight of the incident edges divided by how big the vertices are, so that if these vertices are the result of previous coarsening steps, they'll get penalized more. And then we don't want to do a global re-rate operation after merging 2 vertices, because after I merge 2 vertices, all of the vertices on incident edges could change. Their ratings could change. So instead, what we do is this idea of lazy re-rating, where when we pop from our priority queue, we check if the rating is still valid. And if the rating isn't valid, we just recompute it on the spot and push back onto the queue. So in this way, we never have to re-rank a vertex more than is absolutely necessary. And as I mentioned, initial partitioning we do by running everything 20 times. The algorithms they use are just pick a random partition. BFS half of the graph, starting from a random node, do 9 variations of a greedy algorithm, or you use some other more state-of-the-art algorithms that sometimes give you better results, or your randomness might be lucky and give you something that's even better. That's why we try it 20 times. Now, the problem that we have to solve that remains is, how do we uncourse it? And the way we think about this is that at every step, when I do an uncoarsening, I go from one vertex into 2 vertices, and there is some gain associated with, after I do this uncoarsening, there is a gain of what happens if I move a vertex across the partition boundary. And we do this for every vertex in the graph. So every vertex gets a gain of moving to the other partition, and we build a priority queue over based on these gain values. And then we move the vertex that would give us the most gain across the partition. And gain can be negative, so if the gain is negative, then we would not move that vertex and we would stop. And we do this for some number of vertices per uncontraction. And if we're clever about this, we don't need to fully recompute the gain every time. And I'll very briefly now talk about how the hypergraph data structure is stored. So the idea is that we want efficient contraction of our hypergraph. So the way that they do it is by modeling it as a bipartite graph. So you have vertices on the left and hyperedges on the right. And using this, if you represent it using just adjacency lists, you're able to get good performance for contraction and uncontraction of nodes. So open source, these papers are all by the same university who puts out this package called Ka-Hypar that implements these algorithms, but also does parallelism and is quite fast at hypergraph partitioning. And for our final project, we also made an implementation of the paper in Rust, if you prefer to use Rust. So yeah, that's the presentation. Any last questions? Yeah.
The reason why 20
They found more than 20 had diminishing returns. If you're willing to wait a bit longer, you could do 50. Yeah.
officially test how good the partition is?
They look at the weight of the typical metric that you use is like the weight of the edges that are cut as a fraction of the weight of all edges. Because there's not, for large graphs, there's not really a way to compute like the optimal partition quickly. So you just look at fraction of edges cut, basically. Yeah.
Mention that this was done to optimize code for like loading code on different machines.
Yeah.
Would then this be like dynamic? Like if I move this onto the CPU, the costs for the next instruction will increase, right? Because you don't want to. Because if you have it on the CPU, then even if it's far from the GPU, there's also a cost of moving it from the CPU to the development.
So to handle that, you have to be a bit tricky with your hyperedge construction and also have edges that represent communication complexity. So then the cuts have to account for communication complexity.